Hi, dear audience. I'd like to take the chance to do a quick intro to Force RISC-V instruction stream generator. This is Jinliang Liu Wang from FutureWay Technologies. The Force RISC-V instruction stream generator is available at github.com/openhwgroup/force-RISC-V. It is a powerful verification tool for RISC-V-based CPU design. Is developed and released by IC Lab of FutureWay Technologies, contributed to the OpenHW group under Apache 2.0 license. The Force RISC-V instruction stream generator supports a 64-bit version of RISC-V with RV64I AMA ZICSR FDC extensions, machine, supervisor, user modes. It supports dynamic ISS interaction, dynamic virtual memory management loops, configurable state transition. It has powerful and extensible Python scriptable test template writing framework. Recently, we finished the support for Richter extension version 0.9 and the full paging exception control. Future release will include, but not limited to, advanced memory subsystem verification features, advanced resource dependency, MPMT support, and the 32-bit version of RISC-V. ISG greatly increases verification productivity. This is a general workflow of how Force RISC-V ISG work. On the input side, we have test template that the user written. That will be passed into the Force ISG and control the process of the test generation. While test is being generated, the general instructions will be emulated in the ISS share library to get back the current architecture results. In the end, an executable test case will be generated and passed on to run in a design simulation environment. While instructions are running through the simulation environment, every instruction will be also run on a ISS custom library so that we can interactively cross-check the result. And if there's a mismatch, then we will know there's a bug somewhere, either in the design or in the custom library or even in the test generation. If test templates are written using good dynamic ISGs, a few thousands well-written directed random test templates can cover a CPU design project's test plans well. So by directed random, we mean it's not fully random, but with some user-given general directions for the test to achieve. Over time, abundant good quality, reusable, and flexible sequence libraries will be accumulated and benefit multiple generations of multiple projects. Force RISC-V is a dynamic ISG. On the top left side, we have a very simple test template that basically loop 100 times to first pick a instruction from a low store instructions tree and then generate an instruction. These API calls will call into the Force RISC-V backend. The backend has a lot of structural components like register files, memory model, virtual memory model, exception handlers, and also a lot of test generation controlling features like instruction and operand details, resource dependency, exception trigger or prevent, memory sharing, rounding, data patterns, etc. Through the same API, the Force backend will communicate with a shared ISS library. We happen to pick Spike to use for the ISS share library, and because Spike doesn't have a API interface, we actually put in a API called Handcar API. So while text is being generated on every instruction generated, we'll pass register memory initializations to the shared ISS library and then step the instruction. After the instruction is executed, the shared library will report back register memory rewrites and exception events if there's any, etc. So this way, in any given point of time, Force is aware of the full architecture state so that it can make intelligent decision on test generation and generate very high quality tests, and that can help the user achieve very good coverage results. The design philosophy of Force has many balanced aspects like randomness quality, test correctness, generation speed, scalable design, API synergy, orthogonality, and then also the feedback from user side, feature requests, usability feedback, coverage analysis, and issue report. Awesome results achieved via tireless collaboration from teams on different abstraction layers, but work together the best way they can to achieve maximum force. Force backend is written in C++11 with many deliberately and painstakingly designed implemented testing classes. Close to 75% of code is implemented in the architecture neutral base layer. This enables us to bring up support for new ISAs, for example, RISC-V, much faster since we have built a solid foundation along the way. Effort is continuously made to accumulate architecture neutral functionalities in the base layer. Now let's talk about MPMT support. MPMT is a challenging topic for any CPU project. An entirely different set of problems need to be solved by design verification tools. For ISGs available, options are limited regarding MPMT. Because ISGs tend not to be designed with MPMT in mind, especially at the beginning. But if you don't have that designed well from the beginning, it becomes really hard to retrofit to make it work for MPMT. ISGs tend to not be well suited for MPMT verification due to scalability issues. If the ISG runs are quite slow, then you would need to, when you want to run generate tests for a large thread count, then it doesn't work. It's not an easy problem in general. Force RISC-V ISG is strong in MPMT by design. The design philosophy is originated from heavy MPMT CPU design project. Proven result with CPU product commercially available. We got a rich verification experience in MPMT learned from previous projects. The front end well-designed, transparent threading view make it very easy to design tests with cooperations among threads. All algorithms data structures carefully designed to never sacrifice randomness while maintain very good performance. Force is blazingly fast comparing to other ISGs, thus can scale very well to large thread counts. Thank you for listening to the presentation. Thank you for joining us.